Okay, so first thing we're going to do is look at how to get your polynomial function. So you were each given a table that looked like this. Now the conditions for our polynomial functions was that we wanted it to have an r squared value of 0.99 or higher. Now some of you might achieve this with a linear line because when you're running the marathon you generally tend to keep a constant pace. Some of you might need to go up more. If you get it in the first one, you're going to have to test more polynomials just as proof of concept. So the parts that we really care about is this distance column and this race time column. This tells you how quickly they ran each of the 5 kilometers. So you can see here that it's pretty similar the whole way through until we get to the end and they slow down a little bit. This last one here is much shorter because if you look over here, that distance is only 2.2 kilometers. Okay, so we're going to look at collecting our data from this table. Now, another thing that's important to note is that when we're graphing this, time is always the variable that goes along the bottom. Okay, and we're going to be looking at that in terms of minutes. And distance will go along this column here, and that's going to be in kilometers. Okay. The other important thing that we can take from the task sheet is that we must start at 0, 0 as our beginning coordinate, which means that your time is 0 when your distance is 0. Now, it might be good to have a piece of paper next to you to just note down some little comments as we go through the video so that you're remembering what important things you need to note down. Okay, so we're going to be looking at race time. First one that I need to enter in is going to be, of course, 0, 0, because that is when our time is 0, our distance is 0. Our next one is going to be when our distance goes up to 5 kilometers. So when our distance is 5 kilometers, the time it takes us is 17 minutes. But this is in seconds. Now, if I just put that into Desmos as 14, it's going to think of that as being 14 out of 100 because it's looking at it as a normal number, not as time. So we need to convert this into the fraction of the minute that it is. So to do that, I'm going to take the seconds, 14, and divide it by 60. Now, this process is something that you might want to talk about so that you're evaluating and verifying your process as you go. It's also part of your formulate step. So really, you're doing the seconds over 60 to get the fraction. So if I do that first one in my calculator, the answer I get is going to be 0.23333 recurring. Now, this is the chance where you have to make an assumption or an observation. We've got a number that goes on forever, so we need to choose an appropriate amount to round it to. Now, it doesn't matter what you choose to round it to. You just have to pick something and stick with it. You also should note it down as one of your assumptions. So I'm going to assume that rounding to 2 decimal places will give me accurate results. So the number that I would record over here is 17.23. Okay, and I'm going to do that for all of these numbers in this column here. Now you'll notice that some of these numbers, like this one here, has got the 1 in front for 1 hour. Because we're looking at our time in terms of minutes, we're going to need to convert that into minutes as well. So if you have the 1 in front, you're going to add 60 to this one. Okay, so that one would work out to be 86 minutes plus whatever fraction of time that you have. Okay, so now we're going to go to Desmos. Look at what this looks like when you enter it in. So here is my time column. Now you don't have to change these. You can leave it as X and Y. I just think it makes a better picture. So this is my time column with all of my fractions. Now you can see here that I've put them in as 3 digits, 1 digit, 2 digits, and we agreed that we were going to go to 2 digits. So I'm going to fix that now by rounding the numbers. So this is a 3, it's going to round down. This is a 3, it's going to round down. This is a 6, it's going to round up. This is a 6, it's going to round up. Okay, so now my table is consistent. These ones I get to leave as one place because the number next to it would be 0 and I don't bother writing that. Okay, and now I can record a video. Now I can set my view window. So if I go over here to the little spanner, click that one. Now my x-axis is going to be my time axis. So I'm going to add a label, time, and in brackets I'm going to write minutes. Now if you forget to put your labels on your graph, you will get marked down in the communication section. So it's really important that later you go back and check all of your labels. Okay, now for my y-axis, it's going to be distance. And that's going to be in kilometers. Now to set my view window, I'm going to look over here at the x-axis. I'm going to see what my lowest number is and my highest number. So because this goes from 0 all the way up to 147, I'm probably going to set my view window to be -5 all the way up to 155, just so that when I take screenshots of this, it gets all of the information that I want. So -5 all the way up to 155. And for my y-axis, we're going from 0 all the way up to 42.2. So I might go from -5 again up to 45. And -5 to 45. Okay, and now I can see all of my data is on there nicely. If I want to get a screenshot of this without cutting it, I can go up to this section here where it says share graph, export image, and then normally I right click, copy the image and just paste it in to my Word document. Okay, so we're halfway through our polynomial function. Once you've graphed your data, you need to start testing what kind of polynomial function it can be. Now, there is a specific definition of what a polynomial function is that you should include in your assignment because that will show your terminology in your language. So over here, just like we did in the basketball assignment, you can see that I've got a linear function, a quadratic, a cubic, and if I wasn't reaching that r² value, I would keep going higher until I did hit it. So if I turn it on, you can see the linear function fits or models that data very nicely. You can see that my quadratic is doing the same thing. You can see that my cubic is doing the same thing. So any of these functions, I could argue, are a very good model, but probably for my data, the linear model fits it the best. You would need to make a statement why that is true. Okay, now one other thing that we need to think about, if I look back at the conditions that I set, must start at 0, 0. Now, looking at the polynomial function, if I come over here and I zoom straight in, only one of those none of those functions pass through 0, 0. So currently none of them are meeting our restriction. Some of them are close, but most of them are getting a cheeky head start or they're starting from far behind. So if I want to correct that, all I have to do is think about what role a constant plays in a polynomial function. Currently I've got it there, and I would show these equations with it included, but what happens if you remove the constant from the polynomial function? Good luck.